right, and next up we're going to talk about directional derivatives. And we're going to talk about them for a function f of xy, just because that's more comfortable for us to think about like graphically, but the same formulas will work for functions of 3 variables. So the directional derivative of a function, oops, forgot to close my quotation there, f of xy in direction u, a vector, tells how f changes as you move in direction u. So we learned about partial derivatives, kind of, if we look at the one picture of a surface I've drawn today, df dy tells us how it changes in the y direction, df dx tells us how it changes in the x direction, but maybe you want to know in some other random direction which change you'll see in your surface. And so that's what a directional derivative is for. And you can define it in terms of like a limit definition of a derivative. I'm not going to write that limit. I'm just going to say, imagine taking a tiny step on the surface of f in direction u. What happens? And as that step gets tinier and tinier, your limit definition of a derivative kind of starts to kick in. Instead, I'm going to give you the definition for how you're actually going to calculate it. So we denote it. Oops, everything just fell over here. Okay. We're going to denote it d sub u for the derivative in direction u of f. And it's going to be calculated by grad f dotted with u. For u, a unit vector. Please do not forget that it has to be a unit vector. And to give you some intuition for this, so it doesn't feel like you're memorizing a random formula, I want you to remember that we use dot products Wow, this is super laggy. We use dot products to find projections. Or sort of the component of one vector that runs alongside another. And so for us, we're thinking about the component we care about being grad. Oh, wait, actually not. I don't want to underline that whole thing. I just want to underline one vector. So we care about grad f, which tells us information about our derivatives. And we want to know about it in the direction of u. And that specific component of our derivative vector in direction u is going to give us d sub u of f. So hopefully that makes this random formula make more sense. Also, I'm just going to write right here because there's room for it. If you are not given a unit vector, to turn it into a unit vector, you just divide a vector by its magnitude. And if you go back to the projection formula and kind of like play around with this, then you'll be able to see where the directional derivative comes from. I'm going to try to fix this